Welcome to a specialist mathematics textbook problem work solution. This is looking at chapter 4i, question 11b. So the question asks us to find the distance from 1, 1, 3, which is a point, to the line that's given by the vector equation of x, y, z equals, bracket, 1, negative 1, 2, close bracket, plus t, lots of, open bracket, 2, 3, 1, close bracket. So, the first thing we probably want to do, just for the purpose of simplicity, is to convert to parametric form. This is very easy. We just take the vector equation, as we can see here, and we simply say, well, x is going to be 1 plus 2 lots of t. And we repeat that for all the equations to get them into parametric form, and this way we can find our direction vector. Although our direction vector is actually given in vector equation form, in parametric form we can actually see that the numbers of our direction vector are the coefficients of the t terms. So in this case 2, 3, 1. So now we need to consider the geometric significance of the problem. And in this case we essentially have a point somewhere and we have a line. We can see that line is there, and on that line we have some point A. And then we have some distance between point P and point A. So in context of what we're doing, we're simply wanting to find that distance between P and A, and we're obviously wanting that distance between P and A to be as short as possible. So what we can do is we can find AP. It's relatively straightforward. We know these points, we know what A is and we know what P is based on the previous slide where we worked out the parametric form. So from there it's simply a matter of taking, we have P of x, take A of x, and then we have P of y, take P of y, and we get our new components essentially, as you can see here. Okay, and now what we need to do next is actually evaluate the dot product of the direction vector and the AP vector that we found, and we want to set that equal to 0. And the reason behind this is the fact that they're going to be orthogonal. So if we're looking at the actual point P and the line we want to draw from point P to A, we want that actual line to be, or that line formed there, which is AP obviously, to be orthogonal to the line that we're actually given in vector equation form, because that will be the shortest distance between that point and the line if those two are orthogonal. So in this case, what we do is we evaluate the dot product. It's just a matter of multiplying the components of each of the vectors. So we take AP and we take D and we multiply all their corresponding components together, and we end up with, after simplifying and collecting like terms, as you can see here, just expanding where necessary, we end up with 14 t equals 7, so we end up with t equals a half, and we bring the 14 down to the other side because 7 on 14 is obviously going to be a half. So now for the last phase, what we can do is we can substitute the value of t back into the parametric equations that we found originally. Relatively straightforward. So essentially we've got that point there as being point A, 2, comma, a half, comma, 5 on 2. That's what A is. And from there we can actually work out the distance between the 2 points, because we know what A is, we know what P is. It's just a matter of finding the magnitude. So again, we reevaluate AP. This time we actually know the coordinates of A as numbers. So as a result we get what we can see there. And in order to evaluate the magnitude, we simply get the sum of the x, y, and z differences in A and P, and then from there that's square rooted, and we find that the distance between the points is the square root of 3 on 2 units. Again, that last step is just very simple, finding the magnitude, essentially, which is the length between those 2 points. And that's all for this question. Hopefully you found this interesting and relatively straightforward to follow. Thank you.